Hi guys! Magandang araw po sa inyong lahat. This is me, Sean from Keep It Up with Sean, and today we are going to talk about chemical properties of the soil, particularly soil colloids and ion exchange. In the previous videos, we discussed about different physical properties of the soil, and starting today, we are going to talk about the chemical properties of the soils, and it includes mineral solubility, nutrient availability, soil reaction and pH, cation exchange, and buffering capacity. Since medyo malaki siyang na topic, hahatiin ko rin siya para hindi ganun kahaba at hindi kayo mahihirapang intindihin siya. Lahat ng mga reactions na chemical reactions na nangyayari sa lupa, it happens in the soil colloid. What is a soil colloid? A colloid is either organic or inorganic with very small particle size, which is less than 0.001 millimeter or 1 micrometer, and it has large surface area, and there's a lot of electrical charges. So when we say electrical charges, it can be positively charges or negatively charges. We have here cations, which are positively charged ions such as ammonium, calcium, magnesium, sodium, hydrogen, and potassium, and there are more. And we also have anions, which are negatively charged ions such as nitrate, phosphate, and sulfate. So meron pa rin iba, but these are most of the nutrient ions that are essential for nutrient uptake by the plants. What do you think is the net charge of the most agricultural soils? Is it negative or is it positive? Later, sasagutan natin yan. And the electrical charges of the soil affect the attraction and repulsion of the particles towards each other, thereby affecting the physical and chemical properties of the soil. Kaya, importante yung charges, electrical charges na nasa lupa. And this is the colloidal fraction. If we look at the clay particles under the microscope, this is how they look like. Of that portion, we have here the Kaolinite, the micas, Montmorillonite, and we have there the fulvic acid, which is organic colloid. So, titingnan yan natin isa-isa mamaya. So, imagine this is the clay particle. So, this is a clay micelle, and it has external surfaces. If we zoom those picture there, yan, yung nasa gitna. If we zoom that one, we have there the different external surfaces and internal surfaces. So, external meaning nasa labas, internal naman is nasa loob. And in the lower side, we have there negatively charged colloid, and they also have here the adsorbed ions, cations in the solution, and ions and cations in solution. So most of the soil colloids are negatively charged, and because of that, a lot of the cations are being attracted to the negatively charged colloid. Kasi diba, opposite attracts. So pag meron kang negative, nag-a-attract siya ng more positive ions, which are cations. Like for example, potassium, sodium, calcium, magnesium, and these are the nutrients that are needed by the plants. So we can also see there's a cation exchange. So for example, from the calcium, it exchanged to magnesium or magnesium to calcium. So a lot of reactions are happening in the soil colloids. Cations, and there are also some, aside from the cations, we also have anions such as the chloride, nitrate, for example, the negatively charged, the sulfate, are also present in the solution. This is a table showing you the selected cations and anions commonly adsorbed to soil colloids, which are important in plant nutrition and environmental quality. So you can see here, ions marked by an asterisk are among those that predominate in most soil solutions. But then some of the ions are there, they are present, and they may be important in certain situations, but some of them are also toxic to plants. So like for example, we have here ammonium, aluminum, calcium, cadmium, cesium, copper, hydrogen, so a lot. And then we have here arsenate, borate, and so it depends upon the parent materials in which your soil is being developed. So kasi most of the rocks that are weathered contains a lot of nutrients. And that's why nagkakaiba ngayon yung fertility ng lupa. Some of them can be very toxic, lalo na pag madami yung kanyang quantities. And it will affect the plants or even the microorganisms present in that area. As I've told you, there's a lot of nutrients present in the soil, but these are some of the selected cations and anions commonly adsorbed to soil colloids and important in plant nutrition and environmental quality. So, hindi yan lahat nakasama dyan kasi selected lang yung isinama sa table na to. There are different kinds of soil colloids. We have two, organic colloids and inorganic colloids. Organic colloids includes humus, yung sa organic material, humus, and inorganic colloids are clay colloids, which are divided into three groups. So we have here for the inorganic colloids, we have the layer silicate clays or the phyllosilicates, which include kaolinite, illite, Montmorillonite, vermiculite, and smectite. And we also have oxide clays with iron and aluminum oxides. Example of these are goethite, hematite, and gibbsite. And we also have amorphous clays, which are alophanes and immogolite. Later, isa-isahin natin yan yung bawat grupo na yan. So this is humus, which is an organic colloid. And this is the structure of humic acid. So don't ask me, guys, about the chemical formula of this because I'm not really fond of chemistry. But this is how humic acid, the structure of humic acid looks like. And this is humus is made of humic and fulvic acids. And this is the most complex organic molecule found in soil. And as a result, it is the most stable organic molecule. So we have here different, there's also a lot of charges there. So meron kang positive at saka meron ka rin mga negatively charges. So we have the hydroxyl, hydronium, and there's other chemical present. It's the genesis of the clay minerals, how it is being formed. The silicate clays are developed from the weathering of a wide variety of minerals by the two distinct processes. So we have two processes here, which involves alteration and recrystallization. When we say alteration, there is a slight physical and chemical alteration of certain primary minerals. And the second process is the recrystallization, the composition of primary minerals with subsequent recrystallization of certain of their products into the silicate clays. So when we look at the table, the figure, you already seen or hear these primary minerals here on the left side during I think the first few videos when we talk about the parent materials. So we have there micas, biotite, feldspars, augite. These are mostly found minerals in the primary minerals found in rocks. And these are the primary aluminosilicates. So this is the origin. When we say microline orthoclase, they are very high in potassium, like muscovite micas and biotite. And then we also have here primary minerals, which are high in magnesium, calcium, sodium, and iron. So we have there biotite, primary chlorite, soda lime, feldspars, augites, hornblende, and others. Through time, through different factors affecting them, it will undergo weathering. So I hope you understand what is weathering and how it works. And some of these rocks and minerals present there, they are going to be transformed, altered. So it can be, like for example, when we go to the microline orthoclase and others, you see there's an arrow there. So some of this, like for example, that one, they are going to have to be developed into fine grain micas, which can be illite, or they can also be formed into vermiculite, or they can also be formed into clay chlorite, for example. So if for the case of the others. So there will be transformation depending upon what processes did it undergo. And then if you go there, there will be much magnesium in weathering zone, and then it will turn into smectites or Montmorillonite. And if there's a lot of rapid removal of bases, there will be kaolinite. And pag medyo basa at mainit yung climate, there will be a lot of removal of silicons, and it will now develop clay oxides of iron and aluminum. When we go down, those minerals which is high in magnesium, calcium, sodium, and iron, it's still the same. So like for example there, these minerals, yung primary chlorite, biotite, soda lime, feldspars, augite, it will also be transformed into vermiculite or clay chlorite. And if there's slow removal of bases, it will turn into smectites or Montmorillonite. And if there's kaolinite, rapid removal of bases will turn into kaolinite. And if there's a hot, wet climate, it will turn into oxides of iron and aluminum. So this is how the clay minerals are being developed. But it doesn't happen overnight. It takes hundreds or thousands of years for that soil to become clays, and this is affected by different kinds of processes. So the basic structural units of layer silicate clays, by the way, phyllosilicates is coming from the word phyllon, from Greek word phyllon, which means leaf, because of their leaf-like or plate-like structure. When you look at the picture of how they look like in the microscope, they look like plates na naka-patong-patong. And these are made up of two kinds of horizontal sheets, nakahiga na mga sheets. The one is dominated by silicon, which is called silica tetrahedron, and the other is by aluminum or magnesium, which is called alumina tetrahedron. So what is silica tetrahedron? This is the silica tetrahedron. This is the basic building block of all silicate minerals. It is composed of one silicon, yung nasa gitna, which is blue, atom surrounded by 4 oxygen atoms. So, apat. So, one silicon with 4. So, tetra is 4. So, kaya siya tinawag na silica tetrahedron. So, one silicon atom surrounded by 4 oxygen atom. So, it has a 4-sided configuration, an interlocking array or a series of these silica tetrahedra tied together horizontally by shared oxygen anions gives a tetrahedral shape. This is the silica tetrahedron. When we look at that alumina octahedron, this is an aluminum or magnesium ions are the key cations surrounded by 6 oxygen. So yung nasa gitna niyan, it can be aluminum or magnesium, and they are surrounded by 6 oxygen or hydroxyl group, giving an 8-sided building block termed octahedron. The numerous octahedra is linked together horizontally, comprise the octahedral sheet, and the aluminum-dominated sheet is known as dioctahedral sheet, and the dominated by magnesium is called a trioctahedral sheet. The distinction is due to the fact that 2 aluminum ions in a dioctahedral sheet satisfy the same negative charge from surrounding oxygen and hydroxyl as 3 magnesium ions in a trioctahedral sheet. So, ito yung kanyang structure ng alumina octahedron. So, you can see here, we have here the tetrahedral unit. This is silicon surrounded by 4 oxygen. And we have here the octahedral unit, which is either aluminum and or magnesium surrounded by 6 hydroxyl group or 6 oxygen. And these two, the tetrahedral unit and the octahedral unit, are the fundamental structural unit of silicate clays. These sheets are bound together within the crystals by shared oxygen atoms into different layers, and the specific nature and combination of sheets in these layers vary from one type of clay to another and control the physical and chemical properties of each clay. Kaya ngayon, later, titingnan natin kung ano yung mga different kinds of clay. Because some of these clays have different arrangement and different combination of these tetrahedral and octahedral sheets. Para mas madali nyo siyang maintindihan, this is the tetrahedral and octahedral sheets. Let's represent silica tetrahedral sheet by this, the silicon. Yung green, flat siya. That is the silica tetrahedral. And the aluminate octahedral sheet is represented by the yellow one, which is pahiyo siya, aluminum. Okay. Then, this is the basic phyllosilicate inorganic colloid. So, we have there the tetrahedral sheet and the octahedral sheet. So, alam nyo na, tetrahedral sheet is 1 silicon surrounded by 4 oxygen. In the octahedral sheet, we have there 6. It can be aluminum or magnesium, or aluminum and magnesium surrounded by hydroxide or oxygen. Pile siya dyan. So, for example, we have here tetrahedral sheet. Below the tetrahedral sheet, we have the octahedral sheet and the tetrahedral sheet. And some of these are layers and layers. And depending upon the composition of the layers, will now give rise to the kind of clay that is going to develop in your soil. This structure, we may not see them in naked eyes, but when we look at the microscope, how clays are being formed. This is also a table giving you the ionic radii of elements found in silicate clays, and an indication of which are found in the tetrahedral and octahedral sheets. So for example, we have there the silicate with their valence, with their charges, aluminum, iron, magnesium, zinc, iron, sodium, calcium, potassium, oxygen, and hydroxyl. So we have here silicon and aluminum and iron can be found in the tetrahedral sheet. And then some of them can be found in the octahedral sheet. And some of them are in the exchange sites. And some of them are found in both sheets. And that the radius of each element has a very big role in where they are being found. So note that aluminum, iron, oxygen, and hydroxyl can fit in either. So they can go anywhere. Nasabi ko kanina that there are different classification of layer silicate clays, and this is based on the number and arrangement of tetrahedral, the silica, and the octahedral, the alumina magnesia sheets contained in the crystal units or layers. The silicate clays are classified into 3 different groups. We have here 1:1 type clay minerals, 2:1 type clay minerals, 2:1:1, or 2:2 clay minerals. Ano yung mga type na yan? So, we know that the basic building blocks of the layer silicate clays are the tetrahedral and the octahedral sheets. Silica tetrahedron and the aluminum octahedron. The layer silicate minerals are sometimes defined on the basis of the number of certain positions occupied by cations, and when 2/3 of the octahedral positions are silicate clays are occupied, the mineral is called dioctahedral, and when all 3 positions are occupied, it is called trioctahedral. You have seen this figure before during the genesis of the clay. So this is how the clays are being developed during weathering and during time. So depending on the factors affecting the clays, it will be developed into, and the nutrients that are present there, they are going to develop into different kinds of clay. It can be illite, vermiculite, Montmorillonite, Kaolinite, or oxides of iron and aluminum. Or it can be the amorphous and the olefins. Sabi ko na ngayon kanina. So, for example, balikan lang natin sa glit. Alteration is an example of that would be The change from Muscovite mica to fine-grained mica through physical breakdown, and there will be loss of some elements and addition of others. The second one is recrystallization, in which results from the complete breakdown of the original crystal structure and regrowth of clay minerals. And the relative stages of weathering, fine-grained micas are an early stage, while kaolinite and iron oxides are late stages. So, yun yung genesis ng soil colloids. These are the important clay minerals: kaolinite, which is very most common in soils; smectites, these are shrink-well clays, which includes Montmorillonite. We also have vermiculite, micas, which are fine-grained micas, elite, chlorite, and the humus, which are source of organic matter and the humic acid. So, isa-isahin natin yan, yung mga different types of silicate clay minerals. The first one is 1:1 type silicate clay minerals, which is kaolinite. This consists of one layer of silica tetrahedron and one layer of aluminum octahedron. So, yun siya. The layers are held together tightly by hydrogen bond to restrict the expansion and limits the reactive area to external surface. So, these two layers, the tetrahedral sheet and octahedral sheet, meron siyang bond, like paste or glue na nakadikit sa dalawang layer na yan, which is caused by an hydrogen bond, which is very, very strong. Kaya kahit pa mabasayan ng tubig, it will not expand. And it limits the reactive area to external surface. So, hindi basta makapapasok yung other elements or other ions because it is protected by the hydrogen bond. There will be no substitution of ions or ion exchange because of the hydrogen bond that is present between the two layers. The two sheets are held together by oxygen atoms that are usually shared by silicon and aluminum. So, because of the hydrogen bond and because of its very strong bonding, there is a little isomorphous substitution. It has low colloidal property, the capacity to absorb cations. It is highly impermeable, so water cannot permeate the layers to cause expansion or contraction with wetting and drying. And it has a low cation exchange capacity, which is an indicator of the fertility, how fertile is your soil. So the CEC content of kaolinite is only 6 to 15 milliequivalent per 100 gram of soils. So this is the kaolinite. So we have here one layer of tetrahedral unit, and we have here one layer of octahedral layer. This is how kaolinite clay mineral looks like. So we have different layers of this, one layer of tetrahedral and one layer of octahedral sheet. And because of the hydrogen bonds, which is very, very strong, it becomes a stable clay mineral joined strongly by the hydrogen bond, and there will be no easy separation of these layers. So this is how kaolinite looks like in the microscope, and because of the strong binding forces between their structural layers, kaolinite particles are not readily broken down into extremely thin plates, and it exhibits very little plasticity, the capability of being molded, cohesion, shrinkage, and swelling. So it doesn't swell, it doesn't shrink, and it has low cation exchange capacity. Then we go to the 2:1 type, which consists of one layer of aluminum octahedral sheet, sandwiched in between by two silica tetrahedral sheets. So 2:1. Two silica tetrahedral sheet with one aluminum octahedral sheet. There are two kinds of 2:1 type minerals. The other one is expanding type, and the other one is non-expanding type. So silang dalawa have both two silica tetrahedral sheets with one aluminum octahedral sheet, pero yung isa nag-expand, yung isa naman hindi siya nag-expand. Why? This is how 2:1 expanding type looks like. Because of the bond that is weak, some cations can be replaced. So there will be isomorphous substitution that is going to happen. So the layers are held loosely by weak oxygen to oxygen bond and cations or linkages. And because of that, exchangeable cations and water molecules are attracted between layer, causing the expansion of the layers or lattice when they are wet. The plate-like crystals and much smaller than kaolinite. So dahil hindi nga siya ganun ka-strong yung kanyang bond, so unlike in kaolinite which has hydrogen bond, here is the bond is oxygen to oxygen bond. And because of that weak bond, there will be attraction of cations and water molecules between the layers. Yun, sa in between nila, yung sa mga spaces na yan. And because of those water and cations coming in or coming out, it has the tendency to expand and it's going to swell or shrink. It has larger specific surface area due to contribution of internal surfaces. Soils with high Montmorillonite crack markedly upon drying and tend to be impermeable when wet. Montmorillonite can hold more water than its volume, and it derives its negative charges from the isomorphous substitution of magnesium for aluminum in the octahedral sheet. It shows high cation exchange capacity because it exchanged because of the bond, the oxygen bond. And there will be isomorphous substitution, and it has high swelling and shrinkage properties. The wide cracks commonly form in smectite-dominated soils, like vertisols, when dried, and the dry aggregates or clods are very hard, making such soils difficult to till. Then we also have vermiculite, another kind of 2:1 expanding type. Vermiculite derives its negative charges from the isomorphous substitution of aluminum for silica in the tetrahedral sheet. So yung silicon was substituted by aluminum. And since nagkakaiba yung charges, it will also cause another negative charge. Water molecules, along with other ions, act as a bridge holding the unit together rather than apart. Vermiculite swells less than Montmorillonite, and it has high CEC, around 80 to 100 milliequivalent per 100 gram of soil, and has even higher cation exchange capacity than all other silicate clays, including Montmorillonite and other smectite, due to very high negative charge in the tetrahedral sheet. So the more negative is your soil colloids, the more it can absorb a lot of cations. So mas mataas ang CEC ng vermiculite compared to Montmorillonite. Then we also have another sort of type of clay colloid, which is the 2:1 non-expanding type. Hindi siya nag-expand. And that includes ilites and micas, the biotite and muscovite. Here, the crystal occurs as irregular flakes. The unit layer are held together by potassium ions. So kanina sa kaolinite, it was held by hydrogen bond. In the Montmorillonite and smectites and vermiculite are held together by oxygen bond, oxygen-oxygen bond. But here, oxygen bonded by potassium and oxygen bond. So in between those oxygen bond, merong potassium, which is created, so there will be no expansion upon wetting because of those potassium. The potassium thereby act as a binding agent, preventing expansion of the crystal. Hence, fine-grained micas are quiet, non-expanding. Hindi siya nag-expand because there is a potassium in between the weak oxygen-oxygen bonds. If all or most of potassium is removed, kung tanggalin mo yung potassium na yan sa bond na yan, elite becomes vermiculite. So, that's how clays happen. Tingnan mo yung figure na yan. We have here elites. But then if you are going to remove those ylites, because this ylites is connected by potassium with bonded with oxygen, and because of that potassium, it holds the two layers, causing them to not to expand. But then if you remove that potassium, it will now result to vermiculite. Because the bond is weak, the oxygen-oxygen bond, a lot of ions can now be exchanged. So there will be potassium or magnesium that can be present in the soil, and your layer can now expand. Then we also have 2:1 or 2:2 non-expanding type, which includes chlorite. Chlorides are basically iron magnesium silicates with some aluminum present. Thus, the crystal unit contains two silica tetrahedral sheets and two magnesium-dominated trioctahedral sheets, giving rise to the term 2:1:1 or 2:2 type structure. The 2:1 layer alternate with the hydroxide sheet, commonly dominated by a magnesium. And there is no water adsorption between the chloride crystal units, which account for the non-expanding nature of this mineral. So, hindi siya nag-expand. Then, aside from those layers of clay colloids, we also have sesquioxides, clays, or the oxide clays, which are mainly iron and aluminum oxides. These are caused by extensive leaching and rainfall and long time intensive weathering of minerals in the humid, warm climate where you can find a lot of rain and high temperature, wherein the most of the silica and alumina in primary minerals are dissolved and slowly leach away. And what is being remained in the soils are called sesquioxides, mainly coming from iron and aluminum oxides, which have lower solubility. These are common in highly weathered soils like ultisol and oxysol. Oxides of iron includes goethite, limonite, hematite, and magnetite. And the oxides of aluminum includes gibbsite, boehmite, and alumina. It has low cation exchange capacity, and they are pH dependent. They have high phosphate fixing capacity, which has high phosphorus adsorption capacity. It has stable aggregates and exhibit low plasticity. The infiltration of water is rapid, and these oxide clays do not swell, and they are not sticky. Then we also have another kind of inorganic clay colloids, which are the amorphous clays. These are mixtures of silica and aluminum. It includes allophane and immogolite, and they are common in soils developed from volcanic ash or andesol. They have high anion exchange capacity or even high cation exchange capacity. And almost all of their charge is from accessible hydroxyl ions, which can attract a positive ion or lose the hydrogen attached. This table compares the different properties of silicate clay minerals. So we have here the property and the kind of clay minerals. So we have Montmorillonite, Illite, and Kaolinite. The structure, the shape, the total surface area, the cohesion, plasticity, and swelling capacity, the internal surface and the external surface, the cation exchange capacity, and the anion exchange capacity. For the Montmorillonite, we know that Montmorillonite is 2:1 type, which expands. Illite is 2:1, but doesn't expand, non-expanding, and Kaolinite is 1:1, no expansion. So here, for Montmorillonite, the substitution in octahedral sheet by magnesium or iron. In Illite, there will be a substitution in tetrahedral sheet by aluminum. And Kaolinite, there will be no substitution. The shape are all irregular flakes for Montmorillonite and Illites. Kaolinite are hexagonal crystals. The total surface area for Montmorillonite is 700 to 800 square meter per gram of soil. And we have here 100 to 120 and 5 to 24 For kaolinite, we have for the high, Montmorillonite has high cohesion, plasticity, and swelling capacity. It swells and expands. Elite has medium and kaolinite has low. The internal surface and internal and the external surface from Montmorillonite is very high. Medium for elite and kaolinite is not at all. And because of those properties, Montmorillonite and Vermiculite has higher cation exchange capacity. Elite has 15 to 40, and kaolinite has very low cation exchange capacity. Montmorillonite has low anion exchange capacity. Elite has medium, and the kaolinite has high anion exchange capacity. So this is the comparison of these different kinds of clay colloids. What are the important characteristics of soil colloids related to chemical reactivity? First is the fineness and large specific surface area, and the presence of electrical charges. Because the more fine and high and large is your specific surface area, the more reactive is your soil. And the more the presence of these electrical charges will give you the capacity of the soil to attract those cations and anions. Opposite attracts. So like poles, they repel, and the opposite poles, opposite charges attracts. Imagine this is your soil and you have a lot of negative charges, which is unideal. Since negative yung soil colloid mo, those sodium can be attracted to the soil colloid. Calcium can also be attracted to the soil colloid. Magnesium, potassium, and ammonium can be attracted to the soil. But take note that, for example, chloride, which is negative charges, nitrate, and sulfate can be repelled in the soil colloids. What are the main types of negative charges? We have permanent charge and pH-dependent charge. Permanent charge happens due to the imperfection in their crystal structure and the isomorphous substitution. pH-dependent charge is due to the neutralization of weakly acidic hydroxyl groups. And these are the sources of negative charge. First is isomorphous substitution. And the second is the exposed hydroxyl at broken edges of crystals. Isomorphous substitution happens when there is a substitution of one ion for another of similar size within a crystal lattice. The major source of negative charge in 2:1 layer silicate clays are aluminum for silicon in the tetrahedral sheet, or the magnesium ion for aluminum in the octahedral sheet. And because of the substitution, it will create now more negative charges. The second one is the exposed hydroxyl at broken edges of crystals. At high pH, the hydrogen of these exposed hydroxyls dissociates, and the surface of the clay is left with a negative charge of the oxygen ions. And this type of negative charge is called variable or pH-dependent charge. And also, there will also be functional groups of organic colloids like carboxyl group, phenolic, and alcoholic hydroxyl, which is also another source of negative charge in these colloids. But then there's also a source of positive charge, and this can be due to the protonation of exposed hydroxyl groups and NH2 groups in the case of organic colloids. So, general remarks for this. Generally, agriculturally important soils possess net negative charge. The negatively charged colloids attract cations which become adsorbed on the surface. In humid regions, for example, maraming ulan, malimit umulan, we have there the hydrogen and the aluminum is more attracted than the calcium, than the magnesium, than the potassium, and than the sodium. Pero when you go to arid regions are areas which has less rainfall and mainit yung lugar. Calcium is being absorbed, magnesium, sodium, potassium, and hydrogen. And the order of adsorbability or replacing power of cations commonly found in soils is this. So hydrogen and aluminum is first adsorbed, followed by calcium, followed by magnesium, followed by potassium, which is equal to ammonium, and followed by sodium. So these are the remarks about soil colloids. What are the factors affecting strength of absorption? Bakit nagkakaiba ngayon yung strength? Bakit yung isa mas naunang i-absorb? Bakit mas madali siyang ma-absorb? Bakit yung hydrogen and aluminum mas madali siyang ma-absorb kaysa calcium or kaysa yung calcium mas madali siyang ma-absorb kaysa magnesium? This is because of the charge or the valence. The higher the valence, the stronger the adsorption. Another factor is the ionic sizes, the radius. The smaller the size of the ion, the stronger is the adsorption. The hydration of ion, the smaller the hydrated size, the stronger the adsorption, and also the concentration of solution. The higher the concentration, the stronger the adsorption. Kaya iba-iba yung absorption capacity ng bawat ions. Then we'll go now to the ion exchange. We have two types of ion exchange. Cation exchange and anion exchange. Cation exchange is the attraction of cations, which are positively charged ions, on the surface of colloids and exchange for ions in the soil solution, like ammonium, calcium, magnesium, sodium, hydrogen, and potassium. Samantalang ang anion exchange, this is the attraction of anions, which are negatively charged ions, on the surface of colloids and exchange for ions in the soil solution like nitrate, phosphate, and sulfate. The ion exchange reaction is instantaneous. Ibig sabihin tuloy-tuloy. Reversible. Reversible is from X to Y or from Y to X. Vice versa. Stoichiometric, meaning 1 milliequivalent of one cation is replaced by 1 milliequivalent of another cation. It should be balanced. 1 MEq of particular ion is equivalent to 1 MEq of another cation. The principles governing cation exchange reaction is the reversibility. A cation is usually replaced by a hydrogen ion, and this reaction is reversible. And we also have charge equivalence. Exchange take place on a charge by charge basis. And the ratio law. The amount of exchangeable cation in the soil solution will affect the ion's equilibrium. And we also have mass action, which is if a product precipitates, volatilizes, or strongly associates with an anion, the reaction is not reversible. And there will also be cation selectivity. The higher the charge and hydrated radius affect the exchangeability of cations. For sure, this is not the first time that you have seen this periodic table of elements. And you can find here the different kind of elements with their atomic number and their atomic weight. But not all of these elements are essential for plants or essential to us people. Some of these elements are radioactive, and when the quantities of these elements are higher, it can be toxic to us, to the plants, and even to the animals. We need this one to calculate for the milliequivalents. And the concept of milliequivalent is the weight of 1 milliequivalent is equal to the atomic weight divided by the valence times 1000. So for example, when we calculate the 1 milliequivalent of calcium, note that the calcium has 2 valence, 2 plus. And this is the atomic weight of calcium, 40. So 40 divided by 2, which is the valence, times 1000. So 1 milliequivalent of calcium is equal to 0.02 gram per milliequivalent. equivalent. And this is the Millie equivalent of common cations. So we have here sodium, potassium, calcium, magnesium, aluminum, and hydrogen. So you know how to calculate them. You look at the Millie equivalent weight, nagkakaiba-iba siya kasi nagkakaiba yung kanyang atomic weight and then nagkakaiba din yung kanyang charges. We have here a problem, sample problem. Calculate the weight of calcium needed to replace 1 gram of hydrogen. So how much do we need of calcium? How much gram of calcium do we need to replace 1 gram of hydrogen? Remember that the one quality of ion exchange is that is stoichiometric. Dapat equal siya. Dapat kung 1 milliequivalent of calcium is equal to 1 milliequivalent of hydrogen. So dapat same siya, equal siya dapat para hindi bias yung kanyang ion exchange. So to calculate in this problem, to calculate the weight of calcium needed to replace 1 gram of hydrogen, so we have here the milliequivalence of calcium, and then we compared to the milliequivalence of hydrogen. So if we have that one, to calculate, we need 20 gram of calcium to replace 1 gram of hydrogen. We go to cation exchange capacity. This is the capacity of a soil to absorb and exchange cations, and it is the sum of all exchangeable cations adsorbed in a soil expressed in milliequivalents per 100 gram of soil or in centimole per kilogram soil, and it indicates the fertility of the soil as it reflects the capacity of the soil to retain nutrients. So don't forget it, guys, cation exchange capacity. We have here the table problem siya. Calculate the CEC of this given soil with the following analysis. So we have here potassium, magnesium, calcium, sodium, aluminum, ammonium, and hydrogen. And this is the milliequivalents per 100 gram of soil. So this is the result of your soil lab analysis. So to calculate the CEC, we just sum all of those cations present in the soil. So when you sum it up, it will result to 33.73 milliequivalent per 100 gram of soil. Then we have another problem here. What is the weight of 4.5 milliequivalent potassium in 100 gram soil in a 1 hectare with 20 centimeter depth with a bulk density of 1.35 gram per cubic centimeter? Note that the 1 hectare is equal to 10,000 square meter. For the solution, we have to calculate first the weight of 1 hectare of soil. So we have here 1 hectare is, we know the area, which is 10,000 square meter, and we also have the depth. So when we multiply the area times depth, then we have the volume of the soil. So in this case, we have 2,000 cubic meter. And since we have the bulk density, we just multiply the bulk density and the volume of the soil. By the way, the bulk density is calculated in gram per cubic centimeter. So, kinonvert lang natin siya into megagram or tons to convert it to tons per cubic meter para same yung kanyang unit with the volume of the soil. So, the 1.35 gram of cubic centimeter, 1.35 gram per cubic centimeter bulk density will give you a 1.35 tons per cubic meter. So, you have now the same unit with the volume of soil and the bulk density of the soil. So you just have to multiply that, and to calculate the weight of your 1 hectare soil is you just multiply the 1.35 tons per cubic meter times the volume of your soil. So 1.35 megagram or tons per cubic meter times the 2,000 cubic meter will give you a result of 2,700 megagram per hectare or 2.7 million kilo per hectare or 2,700 tons per hectare. Hindi pa tayo tapos guys. So this is just a calculation of the weight of 1 hectare of soil with 20 centimeter depth with bulk density of 1.35 gram per cubic centimeter. Remember yung question, ano ang weight ng 4.5 milliequivalent potassium in 100 gram of soil. So, for that, i-calculate natin. So, meron tayong 1 milliequivalent of potassium. So, we just follow the formula before. So, 39 divided by the valence times 1,000. So, we have 0.039 gram per milliequivalent. So, you just multiply the 0.039 gram milliequivalent times 4.5. But then take note that is per 100 gram of soil. So, this is the gram of potassium per gram 100 gram of soil. So para isa yung kanyang unit, we're going to convert it into first from gram to kilo, and then when we already have our values in kilo, then we can just multiply it now to the weight of the soil, which is expressed in kilo per hectare. So when you summarize it all, and when you follow the calculation, the 4.5 milliequivalent potassium in a 100 gram of soil will give you a 4.738.5 kilogram of potassium per hectare of soil. So, ganun kadami yung inyong potassium kung sa isang hektarya yung inyong ikakalculate. And the CEC indicates the fertility of the soil as it reflects the capacity of the soil to retain nutrients. What are the factors affecting cation exchange capacity? First is the soil texture. Soil texture is very, very important. The finer the texture, the higher the cation exchange capacity. So clay has higher cation exchange capacity than sandy soils. Second is the amount and type of clay. The higher the amount of clay, the higher CEC. The more Montmorillonite type, the higher CEC. Or even vermiculite has the highest CEC among the clay colloids, higher than the Montmorillonite. And also the amount of organic matter. The higher the organic matter, the higher the CEC, and the higher the pH, the higher the CEC. A high CEC value, for example, greater than 25, is a good indicator that a soil has a clay content and organic matter content and can hold a lot of cations. Soils with low CEC, like for example less than 5, is a good indication that a soil is sandy with little or no organic matter that cannot hold many cations. This is a comparison between a CEC of 25 and a CEC of 5. So CEC of 25 has more clay, more positions to hold cations. So because of its highly negative charge, there will be a lot of cations that will be absorbed compared to the CEC with 5. So more clay, more positions to hold cations. In low CEC, it has low clay content. There will be fewer positions to hold cations. And here, there are some practical applications. So, soils with CEC, which is around 11 to 50 range, has high clay content, more lime required to correct a given pH. It has greater capacity to hold nutrients in a given soil depth. There will be a physical ramification of a soil with the high clay content, and it has a high water holding capacity. On the other hand, soils with CEC ranging from 1 to 10, it has high sand content. The nitrogen and the potassium leach more likely. There will be less lime required to correct a given pH. There will be a physical ramification of a soil with a high sand content, and it has a low water holding capacity. And how do we determine CEC? The method that we use there is the ammonium acetate method. The amount of ammonium is a measure of the CEC. Then we have another problem here. A 100 gram of soil absorb 0.27 gram of ammonium. So during the analysis with ammonium acetate method, calculate its CEC. So to calculate, same. So we have here ammonium is 0.27 gram ammonium per 100 gram of soil. we just calculate with the milli equivalent of ammonium, which is 0.018. So the how to calculate is given below, and it is equal to 15 milliequivalent per 100 gram of soil. And this is a table showing you the CEC and pH in soil orders. So we have different kinds of orders. I hope I will have enough time to discuss these soil orders. Ultisols, alphisols, podosols, antisols, inceptisols, aridisols, molisols, vertisols, and histosols. And we'd have CEC and the pH. So look, histosols has a lot of CEC because these are mostly consist of organic soils. But then the pH is a little bit lower. And this is also the CEC of clay minerals. So we have humus has a lot of CEC, higher CEC, 100 to 300. Vermiculite is around 80 to 150. Montmorillonite is 60 to 100. The hydrous mica is 25 to 40. And the kaolinite is 3 to 15. So mas mababa yung kaolinite. Pinakamataas ang humus followed by vermiculite. And this is also the relation of CEC to pH. So we have here cation and anion exchange capacity, and we have here the soil pH. So you see, as the soil pH increases, the cation exchange capacity also increases. But then it has an inverse effect with the anion exchange capacity. As your pH increases, the cation exchange capacity decreases. Then we have another chemical property of the soil, and that includes base saturation. This is the percentage of CEC that is satisfied by the exchangeable bases. It includes calcium, magnesium, sodium, and potassium base. So to calculate the base saturation, this is equal to the milli equivalent of exchangeable bases divided by CEC times 100. So in the previous problem on CEC, the base saturation of that soil will be this one. Remember those problem in the earlier slide? So we have here the same data. When we calculate the base saturation, we just include 4.5 from potassium, magnesium, calcium, and sodium. So 4.5, 8.7, 12.54 plus 0.89 divided by 33.73 times 100. So it results to 78.95%. So the base saturation of this soil is 78.95%. Uy, bakit hindi natin isinama ang aluminum, ammonium, at saka hydrogen? Bakit we only consider potassium, magnesium, calcium, and sodium? Because the ammonium, hydrogen, and aluminum are not base, but they are acids. The acidity or alkalinity is governed by the relative concentration of hydrogen and hydroxyl, and the bases tend to form hydroxides: potassium hydroxide, sodium hydroxide, calcium hydroxide, and magnesium hydroxide. And aluminum tends to contribute hydrogen through hydrolysis. So generally, as base saturation increases, pH also increases. Then we also have another topic, which is the exchangeable sodium percentage, or ESP. This is the proportion of the exchange sites occupied by sodium. And this is equal to the milli equivalent of sodium divided by CEC times 100. So in the previous problem on CEC, the ESP of that soil is 0.89 divided by 33.73 times 100, which is equal to 2.64%. Kasi yung sodium niya, ngayon yung kinoconsider. So yan yun siya. And salts with high ESP, greater than 15%, are considered sodic and need to be reclaimed through the addition of gypsum, which is calcium sulfate. So this is just a short presentation, guys. I hope you learned something from this presentation. I will try my best na to catch up and para makahabol before your examination. And please watch out for the next video, which is about soil pH. And if you are new to my channel, please click the subscribe button and it will help me a lot. Thank you very much. Bye.